Alright, so yesterday we left off talking about exponentials. The very last thing we did was we talked about the transformations. So just a quick reminder on that. Anything on the inside is horizontal. Anything on the outside is vertical. Addition is always a shift. Multiplication is always a stretch. Okay? And the horizontal stuff is always the opposite of what you would expect. Vertical isn't. Okay? So just a little reminder about that. Okay, so we're going to look at some problems where we have a population or maybe an amount of bacteria or something like that. Could be doubling, it could be tripling, could be going up like 2% every year, something like that. Those are all examples of exponential problems. In particular, those are all growth. Something doubling, tripling, going up a certain percentage. So we're going to look at an example where we have a population of a city that starts out at P, and it's going to go up at a constant rate. That rate will be given as a percent. We'll say like the town is going to get 3% more people every year. To keep it simple, we're just going to assume that when it gains people, nobody moves out, nobody dies, anything like that. Okay, just a continual growth rate. Obviously, real life, you'd have to subtract for people moving away and stuff like that. So that formula will tell you the amount of people you will have in a town, or whatever, based on a growth rate and how much time has gone by. So this is the amount of, in this case, it's people, so I'll just write people. But it really could be anything. Amount of bacteria, amount of whatever it is. Okay. So it's the initial amount times 1 plus r to the t. Important thing about r is you have to do it as a decimal. So if they tell you it's a growth rate of 5%, r is 0.05. 12%, 0.12. Okay, so that's the exponential growth formula. Now, the exponential decay formula is almost exactly the same thing, except you change one thing. Instead of 1 plus r, what do you think it would turn into for exponential decay? It's going to be minus. Okay, so it's going to be 1 minus r. So an example of that would be, let's say you had a population of a town that was going down 2% every year. Okay? How many people would be left after 50 years? Well, you plug in your time, if it's 50 years, plug in r, 0.02, and then you solve it. Okay? You just have to know how many people you started out with. Okay? So that's your exponential growth and decay formula. Okay? Let's look at an example. We're going to solve this with the calculator. I don't think you'll need it. You can just watch me do it. It's nothing new. All right, so this town has a population of 50,000 people going up at 2.5% every year. Okay. First thing they want us to do is basically write an equation that represents this. And then we're going to use a graph to figure out when the population hits a certain amount. This is actually a pretty common problem. We're figuring out when the population is going to double. Exactly double. All right, so let's just start out by writing our equation, and then we'll figure out how to graph it, and then what we got to look for on the graph. So I'm just going to write. I'm going to write p of t. So my population as a function of the time that has gone by. Okay. What's the first thing that I need in my exponential growth formula? Yep. I need the population. So it says population of 50,000. So we have 50,000 times, and then what goes in the parentheses? 1 plus. Yep, it's 1 plus your rate. And in this case, our rate is 2.5%. So what am I going to put in there again? 1 plus
0.25.
0.25 would be 25%. 0.0, yeah, we need one more 0 in there. So we just take that, move it 2 places to the left. 1 plus 0.025, and I need one more thing. Time, that's my exponent. T. Okay, so let's just simplify that, and just that's about all we can do right now is just combine 1 and 0.025 and put 1.025. So this is the answer to the first part of the problem. So we've modeled the situation with a function. Questions on that? Okay, so now they want to know when the population reaches 100,000. Where would that get plugged in? We can either plug it in for P of t or t. Which one would we plug it in for? Yep. P of t, right? That's your population on the left. So plug it in for your population. So it's going to go right there. And then we'll figure out how we're going to solve it with a graph. You don't have to use a graph. You can use what's called a logarithm. But we haven't learned that yet. So we're going to use a graph. So 100,000 equals 50,000 times 1.025 to the t. Now, Isabel, if I wanted to solve that with a graph, we've done this kind of thing before. What do you think I would do?
You put what's on the right side into the first white, please.
Okay, so I can put 50,000 and then in parentheses 1.025. I have to use x as my variable, but okay.
And then the second one, you put what's on the left side, so 100,000.
All right.
And then you'd see where they intersect.
Yeah, I'm going to see where they intersect. So remember, we're looking for where the population is 100,000. So is keeping my y max at 10 going to work? No, it's going to be a little higher now. So let's put it up to like 120,000. All right. As far as negative people, that doesn't really make sense in this problem. X is your time. Time can't be negative. And I don't know how many years are going to have to go by. Let's just set it up to 50. So we're going to see the population growing, and if 50 years isn't high enough, then we'll do more. Okay, so there's our population growing, and we're going to see a line at 100,000 in a second. We will. There we go. Perfect. So that window is fine. And then what did you say to do from there, Isabel?
See where they intersect.
Yep. So second calc, intersect. There's only one intersection, so the guess doesn't matter. Okay. So it's going to take a little over 28 years for the population to reach 100,000 people, which is doubling. Okay. So about 28.1 years. We're going to do that exact same problem again on either Monday or Tuesday. Exact same numbers. We're going to get the exact same answer. The only difference is we're going to do it with algebra instead of doing it with a graph. Okay.
I already don't like that.
You don't like that problem?
Well, the whole using algebra part.
With algebra, you can do it faster with algebra than you can with the graph.
Look at that.
By the time on your graph, by the time you set your y min, your y max, your x min, your x max, type everything in, wait for it to graph, then go second calc, intersect, first curve, second curve, guess, and all that stuff. I could have solved it by algebra like in half the time because it's not a super huge equation. Sometimes graphing is faster, but it wouldn't be in this case if you knew the algebra part. Okay. Any questions on that? All right. So that's an example of something growing exponentially. Okay. Okay. As always, be careful about negative values. A lot of times negatives don't make sense. Because if it's time, negative doesn't make sense. If it's people, usually negative doesn't make sense. So just be careful about negatives.
So if you get a negative answer, do you just change it to positive?
I mean, when you're putting your y min and your y max. Yeah, so when you're setting your window, a lot of times 0 is usually as low as you want to go. When you're dealing with this, you won't get any negative answers. Yeah, especially if you're solving for time. If you did, something went wrong. Okay, let's look at a specific type of growth, which is doubling. Right? So let's just look at what's happening here, see if we see a pattern. So let's say you start with 100 bacteria, and it's going to double every hour. Right? So after 1 hour, if everything goes according to plan, how many bacteria would I have? 200. Okay. And I want to see the pattern. I want to show you something. I'm going to write it as 100 times 2. Right? How about after 2 hours? How much bacteria would I have? 400, which, again, I'm going to write it as 100 times 2 to the second power. 2 to the second is 4. 4 times 100 is 400. Let's do one more. How many would I have after 3 hours?
16.
That would be 4 hours. I missed one in there. $800. And I wrote that as 100 times 2 cubed. Does anyone notice a pattern there? And I guess this one you could put a 1 on it. Oh, Madison, do you notice a pattern at all?
The exponent is the same in number of
Yeah, the exponent is the same as the number of hours, and it's multiplied by the original amount. So it's the original amount times 2 to the t. There's your formula for something doubling. The original amount times 2 to the t. Now what's important is you put t divided by the length of the time to double. Okay, and if you're looking like, well, you didn't do that up above, I did, but the length of the time to double was every 1 hour. So if it's doubling every 1 hour, it's just t divided by 1. That's all. Okay, and the reason we have to do that is because this thing that I just circled, the exponent, is supposed to represent how many times your thing has doubled. Right? So let's say you had a bacteria that doubled every 5 days, and 15 days have gone by. You don't want the exponent to be a 15. 15 means it doubled 15 times. No. If it's doubling every 5 days, and 15 days have gone by, it's only doubled 3 times. So that's why you put 15 days divided by the length of the time to double, and there's the number of times it doubled. So that's what the exponent represents. How many doublings have taken place? Okay, so let's look at this one. So we've got 100 bacteria. Now this one doubles every hour. So it's kind of like the problem we did up above. I want to know, when will we have 350,000 bacteria? What's interesting kind of about exponentials, you don't realize how fast it grows. You might think, oh, it's 100, it's going to take a while. It's not really going to take that long.
100, 200, 400, 8,000, 800, 1,600.
So let's set up our equation, and then we'll do the same thing we did on the last one. We'll find an intersect. Okay, so the formula, initial amount times 2 to the t divided by the length of the time to double. So the amount in terms of the time. What's the initial amount of bacteria that I have here? 100 times, what number do we put in there for doubling? We put a 2 for doubling. And it's t divided by the length of the time to double. Well, t is what we're solving for. We don't know t. But we do know the length of the time to double. How long is it? Every 1 hour. So in this case, all you need is a 1. So there's your formula. And they want us to know when the amount hits 350,000. So where does 350,000 get plugged in? A of t. Yep. Right there. So it's almost the same thing we did last time. 350,000 equals 100. I'm just going to put 2 to the t. I'm not going to put t over 1 because you don't really need the 1 in this problem. Let's think quickly about time. Does it make sense for time to be negative? Amount of bacteria to be negative? No. So I should set my window minimums at 0. Right? Don't worry about negatives. Y max. Okay. We got to go up to 350,000. So I don't know. I'll go 400,000. That should be fine. Now, t is how much time has to go by. I don't think it's going to take anywhere near 50 hours. If it's doubling every single hour, I bet it's going to hit 350,000 way before that. Right. So let's type it in and see. Doesn't matter which one you put in y1 and which one you put in y2. Okay, so I'm going to put that in y1. I'm going to do 100 times 2 to the x. Remember, you can't use t as your variable. You always have to use x. And let's see what we get. So there's 350,000. There's our bacteria. So very quick. So if it ends at 25 hours, I would say that's less. That's like half. That's maybe like 10 or 11 hours. So it didn't take that long. Okay. It took, let's see, it took 11.8 hours. About 11.8 hours. Right, now sometimes they word it and they say, when will you have more than 350,000 bacteria? If they worded it that way, I would say anytime after 11.8 hours. Okay. But this one said, when will you have exactly 350,000? And you'll have that exactly at 11.8 hours, rounded. Any question on that one? Okay, so both of those examples we just did were growth. Let's look at one that's decay. So decay means what happens over time is the amount of stuff you have is going down. Okay. One thing that we can use decay for is it's called half-life. Is anyone familiar with, not like a game Half-Life, but half-life, what it means in chemistry? Yeah?
Isn't it like chemical has like half as like whatever as it was when it started, like radioactive or whatever?
Yeah. So half-life is the amount of time it takes for half of a substance to break down. All right. Like radioactive waste from like nuclear power plants, sometimes the half-life is thousands of years. So if they produce 200 tons of waste today, maybe in 50,000 years, it'll only be half that. In another 50,000 years, half that. So stuff like that is kind of a problem because it takes so long to break down and be safe. And then some things have extremely fast half-lives. Like sometimes when they try to make things in like a lab and create new elements and stuff, sometimes what they create, it only lasts for like a millionth of a second because the half-life is so fast. Basically, the second they create it, it's gone. So it's really hard to kind of study that stuff because it's not around very long. Okay. So half-life, again, amount of time it takes for half of that substance to basically decay, which basically means disappear. Okay, very similar to the exponential doubling formula. except you put a 1/2 in instead of a 2.
Where does this substance go once it decays?
I think it breaks down into different, like something else. So if you had like a nuclear substance, I don't know what the byproduct is when it breaks down, but it would break down into something that's safe. I don't know exactly what the chemical reaction is, but the stuff is still there. It doesn't disappear. It's just no longer radioactive. Maybe it breaks down something safe. Yeah. Okay. Or you could kind of think of it, this isn't exactly the same thing, but if you think of like water, like in a pot, maybe you check it, and then like you check it later and there's less because some evaporated. Well, it's not that the water just disappeared, it just, it turned into more of a gas and it went into the atmosphere. So same kind of idea, it broke down and it changed into something else. All right, so this particular radioactive substance has a half-life of 20 days, and you're going to start with 5 grams. So after 20 days, you'd have half that. After 20 days, half that. Okay, so we're going to find a formula, and then we're going to use the formula to figure out maybe when we have a certain amount left. Okay, so any exponential formula, first thing you always need, Nick, is what? What's the first thing you always need in an exponential formula?
You need
So when I'm writing this formula, I'm going to put something here.
that would be 5.
Yeah, exactly. You're going to put down your initial amount. So 5 times, and now this is half-life. So what goes in the parentheses? Half. And the exponent is t divided by the length of the half-life. This time the half-life is not 1. The length is 20. So it's t over 20. So that's the answer to that part. Second part, when will there be less than 1 gram left? Well, you can kind of estimate it. After 20 days, you have half of 5, that's 2.5. After another 20 days, you have half of that. That's like 1.25. So it's going to take a little bit more than 2 half-lives. So maybe 50, somewhere around 50 days or so. But let's set it up and solve it. So we want to know when our amount, I'm just going to say equals. I know it doesn't say equals, it says specifically when is it less than. But if I find out when it equals 1, then I can say any time after that, you'll have even less. Okay, because it's going to keep decaying as time goes on. So let's just see when it equals 1. So 5 times 1/2 to the t over 20. Okay, minimums should still be 0, but this time you know a maximum. You don't have to guess. The maximum is going to be 5. I'm never going to get more than that. All right, so let's put that in as 5. As far as the y max, I still need to kind of guess at that. How many days is it going to take? I thought about 50. So I'll go to 75 and we should be safe. Okay. We've got 1. Oh, let's clear that. And then 5 times, for me it's easier to type in a half as 0.5. Raised to the x over 20. Okay, let's see what we got. All right, so I'm going to fix my window because that's, first of all, they're not crossing. I'm going to double check that I typed everything in right, and then I'll check my window. All right, so I've got 1, that's good. I got 5 times 0.5 to the x over 20, that looks fine. Oh, I switched my x and y. So x max is going to be 75. That's days. Y max is going to be 5. Now we should be perfect now. Okay, so there's the amount of substance I have left decaying. And it's going to keep decaying, and it's going to get closer and closer to what? 0, but it's never going to reach it. It's always going to be a little bit left. Eventually, it's so little it doesn't even matter. But it's like it never really goes away. Okay. So do your intersect. And we get 46.4. I thought it was about 50, but 46.4 days. So that was the last part of that section. So if there are any word problems about half-life or doubling on the homework, you should be able to do them now. Any questions on that? Okay, and the homework, that's the same homework. You already have that written down. Does anybody need it again? Okay. All right. So the very last function we're going to look at before we start trigonometry is log functions. We're going to look at log functions over 2 sections. We're going to take 3 days to do the 2 sections. Okay, so we'll do 5.4 part 1. We might run into the same thing that happened the other day. Might not get through the whole thing. I'll give you the homework like I did for the other one, and we'll finish whatever we don't on Monday. But 5.4 part 2 and 5.5 are short lessons, so we'll catch up next week if we don't finish today. So log functions are good to study right after exponentials because they're the opposite, okay, or more specific, they're the inverse. Okay. Remember, inverse of a function is a function that cancels it out. So like square, square root, those are inverses of each other. Cube, cube root. Exponential, log. Okay, they are inverses of each other. So if exponential functions grow extremely fast, and these are the opposite, they grow extremely slow. Okay, log functions are the slowest growing functions we have. They go up very slow. And what I'm going to do is I'm going to show you visually the difference between a log and an exponential. Okay. And what ends up happening is they are mirror images of each other. Okay. In fact, any functions that are inverses are mirror images over this line. Let me show you for a square and a square root. I'll graph both of them and show you how they're mirror images. Now, when you take a square root, you can only take a square root of numbers that are what? Positive, right? So I'm going to look at squaring and square rooting, but I'm only going to look at positives, okay? Only going to look at positives. So the way I can tell the calculator to do that is like this. I'm going to put this in parentheses, and I'm going to tell the calculator only worry about x squared if you're looking at numbers that are greater than or equal to 0. I don't have to worry about that with square roots because it already is part of it. All right. It's just if I'm not going to look at negatives in y1, bless you, I don't want to do it in y2. Okay, I want to compare same thing to same thing. Okay, let's see what it looks like. So there's your square root function. Remember, it has a start point and it goes in one direction. Okay. And just focus, you know what, even to make it simpler for you. Just look at that. And what I'm going to do is I'm going to draw in the line y equals x. And watch what happens. If I were to take the graph in red and fold it on the black line, it would land exactly on top of the graph in blue. They're mirror images. I'm not really showing a nice part of the graph. Maybe this would look a little nicer. There's your square root, there's your other one, and there's your line in black.
But it doesn't look.
Yeah,
It depends on how you look at it.
People see how those would be mirror images? Like if you did fold that piece of paper right on that black line, it would land right on top. I know you got to kind of visualize it, but it would. It would land right on it.
It looks like it's.
And here's an example of an exponential in blue. And this is the first time we've seen a log function, and it's in red. If you were to fold right on that black line, the blue one would land right on top of the red. Okay. Notice the exponential curves up really fast. The red one curves up very slow. Okay, they're opposites. Log functions kind of look like square roots a little bit, but there's a big difference. Square roots have a start point, and they go in one direction. Log functions go down, or if you flipped it, up forever. Okay? Square roots don't have this part right here. Right? So if you got rid of that, and you just kind of said, all right, it starts right here and it goes in one direction, that's more like a square root. Okay? But log functions go down forever, getting extremely close to the y-axis. Does anyone remember what we call that? When it gets really, really close to something? It's an asymptote. So log functions have asymptotes. Exponentials also have asymptotes. The difference is with an exponential, your asymptote is horizontal. Okay. The graph in blue comes down, gets closer and closer to 0, never reaches it. The graph in red curves closer and closer to that dotted line. Okay. So that's the difference between a log and a root. Okay, logs have vertical asymptotes. Roots do not. They just have a start point. But we'll graph a few more later. All right. So when we write logs, this is how you're going to see it written. And the way you pronounce that is y equals log base a of x. There are no exponents in that. Okay, if this was lined paper, it would look something like this. Well, I didn't write it perfectly straight, but if you're putting it on lined paper, it would look something like that. Y equals log. The base A is actually a subscript. It's below the line, and the x is right on it. An exponent would look like this. Like this. Now you have an exponent. So y equals log base A of x. X is called the argument to the log function. An argument is just a thing you plug in. Okay, all the functions we've studied all year have arguments. 5 is the argument to the square root function. It's the thing you plug in. Okay. It's just the thing you plug in. But it's kind of handy to remember the word argument, because when I mention something, it'll help with, you'll see, it'll help you. So just remember the thing you plug in is called the argument. Now, if the base is a certain number, in fact, 2 special numbers, we have a name for it, but only 2 numbers. If the base is 10, okay, that's called a common logarithm, or a common log. And base 10 is one of 2 bases that the calculator can do by pressing a single button. And I'll show you the button in a second.
Aren't all logs based off of 10? Like
No.
there isn't
Yep, go ahead.
there isn't like
like a specific thing goes to it?
Yes. If you don't have something written, like if you just see the word log, all right, all by itself, we assume that it is a common log. I think that's what you were saying.
Yeah, that's, yeah.
So if I just write down on paper, find the log of 5, and you're like, wait, you didn't put a base. You're right, I didn't. So when there isn't, you assume it's 10. Just like in algebra, when you have an x, there's a number in front, we always assume it's a 1 if you don't put anything. Right? So if I go on the calculator, the log button, I can't really show this at the same time. Let's go like that. Okay, the log button is on the left-hand side, right below the x squared button. Log. Right? So if I type in log of 5, the calculator didn't put a base. It gave me some number as an answer. It assumed base 10. Okay, any questions on that? So if the base is 10, it's called a common log. There's one other special base that has a name. This is the only other one. If the base is e. And if you're like, wait a minute, e? Isn't e a letter? No. E stands for a number. Okay. Just like if someone said, well, isn't pi a letter? I would say, yeah, in the Greek alphabet, pi is a letter, but in math, it's not. It stands for something. Okay. It stands for 3.14. Well, someone said, isn't E a letter? Yeah, E is a letter in the English alphabet, but in math, E is used to represent the number about 2.72. It looks like there's a pattern to it, 1828, 1828. It doesn't continue 1828. I don't remember the next number after that, but it changes. Right, so E's not, I think most people have heard of pi. That's used a lot more than E. But E is another number that is used in math, for especially what we're doing right now. So if the log has a base of 2.718, or they just put E, that's called a natural log. Natural logarithm. It is the only other base that you can do on the calculator by pressing a single button. If you want to do a base on the calculator that's not 10, and it's not E, there is no button for it. Okay? There's still a way to type it in. I'm going to show you that some other time. But there's no button for it. Okay? So the ln, or the natural log, is right there. It's right below the log button. It's right to the left of the 4, roughly. So when I type in ln 8, that's called a natural log. Now you might be looking at it like, well, he just said log base e. Well, they don't write log base e, right? That's what it means. But anytime you talk about natural logs, people always use this abbreviation, ln. You'll never see log base e actually written on paper. The only time you'd ever see it is when you're learning right now what an ln is. That's what it means. But that's the abbreviation we use. What's a little tricky about that abbreviation is it hides the base. When you write ln, you mean this, log base e. So you've got to remember that ln means base e, even though it's hidden in that abbreviation. Why didn't they use NL, like natural log? That would make sense. NL. I don't know why they switched it to LN. I'm not sure. Okay. But every calculator, that's the abbreviation, and that's how it will be written. So any question on that abbreviation? LN. Okay. So we'll take a look at something we're going to do quite a bit with logs. Actually, we'll do that in a second. Which is we're going to convert between something that has a log and something that doesn't. Okay, we'll practice that. But first thing is, let me graph one more log function so you can see what it looks like. Okay, and this is going to get into the domain and the range. So I'm just going to graph the common log of x. Okay, I'm doing base 10. Now, going to be careful because the calculator doesn't graph it correctly. Okay, no calculator that I have in here will. I'll graph it like this. If you look at that, where does it look like it's starting? Up at 1?
-1.
Or -1. Yeah, it looks like it's starting at -1. Watch what happens if I zoom in. Let's just zoom in near there. Does it still look like it's starting at -1 or now a little lower? Now it looks like it's starting a little lower. So the calculator can't really draw it perfectly correct. Okay. What it should look like is like this. This part should continue down, getting very close. Right? So log functions always have a vertical asymptote. So they go down forever, or if you flip it, it would go up forever. But this one, the basic one, always looks just like that. So domain, notice it's not going past the y-axis. Kind of runs into a wall right here. Can't go past it. So it doesn't go to the left forever, but does it go to the right forever? What do you think, Sam?
Yeah.
Yeah, it's just going to keep going like this. It's not going to change. It's just going to keep going up. Extremely slow. Extremely slow. Very, very slow. So the domain is from 0 to infinity for the log function. You cannot take the log of a negative number. It doesn't work. If you try it, log -3, I get an error saying that it's imaginary. Okay, we're not dealing with imaginary logs. And the range, well, if I go back to the graph for a second, it doesn't look like it goes up forever, but it does. It never stops going up. It just keeps going up extremely slow. Okay? So it does go up forever, and it's clear from this part, it does go down forever. So that's where your range comes from. All log functions always have the same range. If something goes up forever and down forever, I don't care how you shift it or stretch it or flip it, you can't change that. If it goes up and down forever and you shift it up too, it still goes up and down forever. So you can't change the range of a log function. All right, so what we're going to practice next is converting between log form and exponential form. It's basically an equation that has the word log in it, and then an equation that doesn't. There's no arithmetic to do at all. It's a pattern of where things move. You just have to recognize the pattern. So, for what I'm about to show you, I'm going to use a variable. And the variable is going to represent a positive number, but not 1. Okay, so this formula works as long as you have a positive number, but not the number 1. So what you have on the left, that's log form. What you have on the right, that's exponential form. All right. Let's kind of look at how we can figure out what goes where. So I kind of put colored boxes around things that match up. So the first thing here is A. What is A again? It's the what of my log? Well, it's the low. It's written lower than everything else. So it's the base. Right? It's the base on my log. When I rewrite this without the word log, I'm going to have an exponential. It's going to become the base for the thing that's my exponent. Okay? So the base on the log becomes the base on the exponential. That's the thing that gets the exponent. So the base stays as the base. Right, so the next thing is logs equal exponents. It's important to remember. Logarithms are exponents. So when you go on your calculator and you type log of 8, you hit enter, and you clear what you had before, you get 0.9, you get 0.9 roughly. That 0.9, that number is an exponent. What is it an exponent on? Well, it would have been some problem we would have solved. Okay, but I just want you to understand, when you get an answer to a log, it is an exponent. So logarithms equal exponents. That's why y is the exponent. Now the only thing left is this. That's the thing you plug into the log. What did I call that earlier? The argument. And if you argue with people, you're probably going to annoy them. And when you annoy them, they're going to leave. And you're going to end up by yourself. Okay? So that's how you can remember the argument ends up alone. Or if you have a better way to remember it, then use your way. But that's how I remember it. The argument ends up alone. And actually, you only have to remember where 2 out of 3 of them go, because if you remember where 2 of them go, then there's only 1 spot left for the third thing. Okay. All right, so let's try changing this to an exponential expression. Okay, let's. I'm not going to put colored boxes around every problem, but this one I did. Let's start with the base. What's my base on that log? 3. So when I rewrite it as an exponential, 3 is going to be my base. Okay. The next part. Logarithms always equal what kind of number? Just said that. Logs are
Exponents?
exponents. Yes, logs are exponents. Logarithm equals the exponent. So y is going to be your exponent. All right. And now, there's only one thing left, the x. What's the x called again? It's the argument. What happens when you argue? You annoy people and you end up by yourself. So x goes by itself on the other side. And that's it. You can't solve that. Like if we knew y was 2, then I could plug it in and say 3 to the second power is 9. But that's as far as you can go. Question on that one. Let's try this one. Log base 5 of x. Y equals log base 5 of x. Okay, what's my base there?
5.
Yep. So when I rewrite it, 5 is my base. Okay. Now we're going to put an exponent on the 5. So we look at it. Logs always equal what kind of number? Exponents. Logs equal exponents. There's my exponent. The only thing left is my argument, and the only spot left is by itself on the other side. Okay. So that's changing from exponential to log. Any questions on that? Again, there's nothing you can solve there because you don't know why. So you're done. All right, let's do the opposite. Now we're going to change something to a log expression. Well, if we're going to change something to a log expression, what do you think the first thing I should write down is? This kind of gives it away that it's a log expression. Log. So you're going to start by putting the word log. You can put equals in there too. Okay, let's start with the 1.2. Megan, what's the 1.2? Because it's lower than the exponent. It's the... So in this one, not yet. We're just pretend like we're not even looking at the word log yet. I just want to know what the number lower than the exponent is called. Morgan?
Rate of increase.
No, not rate of increase. So that's with exponential stuff. I know what you mean, though, like if we had a t there or something like that. But just from like algebra 1, like the higher number is the exponent, the number that's lower is
The base.
the base. So 1.2 is the base. Okay, it was the base up above in the original problem. It's the base in my log. Logarithm. How about shy? Logarithms always equal what kind of number?
The exponent.
The exponent. Exponent was a 3. So logarithm equals exponent. The only spot left is for my argument, and the argument is always the thing that was alone. And there's your argument. And that's it. That's how you change from log to exponential. Any question on that one? All right. Let's take a look at this one. E to the B equals 9. E to the B equals 9. I'm going to start by writing log. And Carolyn, what's my base going to be here? E. E is the number that's lower than the exponent. So E is the base. E will be the base. Wait, we've seen that before. Log base E. We'll come back to that in a second. Jake, logarithm always equals what kind of number? Exponent. My exponent is right there. B. The only thing I haven't used is what? The 9. That's the argument because it was by itself. Now, that we wouldn't see because there's an abbreviation. What can I change there? Yeah, we want to change it. Log base E means ln of 9. And now that's one you could type in. If they wanted to know the answer as a decimal, you could press ln 9, hit enter, and it's about 2.2. They didn't ask for the decimal, but I'm just showing you could type it in. Question on that? All right, so this one says to show that that's true. So somehow what's on the left equals what's on the right. There's only one thing we know how to do with log equations so far. What's the only thing I've shown you how to do so far? John?
To graph them.
I haven't shown you how to graph yet. I mean, I did one on the calculator, but we haven't done any graphing by hand yet. So we are going to do graphing, but not today. So what have we done in the last 2 problems so far? We've done what with equations that are in log form? Yeah.
Change that to exponential.
Change them to exponential. It's the only type of examples we've done so far. Change between log and exponential. So let's change that to exponential and see what happens. Can you tell me my base? Isaac?
Sorry. I looked at another problem. 2.
2. Yep. So my base, that's what would be below the line. So my base is 2. Nick, how about my exponent?
Exponent would be 3.
Yep. Logarithms equal exponents. So 2 cubed equals, and then Kylie, what number would have to go on the other side?
8.
I haven't used the 8. Is that true? Does 2 cubed equal 8? Yeah. Then we showed that log base 2 of 8 equals 3. We proved it. Just by changing it to exponential. Let's look at this one. So this is a little different than prove because they don't tell you what it should equal. They tell you it'll equal something, but they want you to figure it out. So Emily, what do you think I'm going to do with that equation since it's in log form? I'm going to change it to exponential. There's my base. Logarithms equal what kind of number? Exponents. So my exponent there is x, and the argument ends up by itself on the other side. Now, from this part, we got to do this in our head. If you're not sure what that would be, bless you.
Thank you.
Look at that problem. It's almost the same thing. 5 to what power would be 25? Yeah.
To the squared.
Squared, yeah, to the second power. Now, this isn't 25. We want 1 over 25. Does anyone remember what kind of exponent you need to have here to make this flip? Yeah?
A negative exponent?
A negative. So the answer here isn't 5, it's negative 5. Right? So you want it to be 25, but you want it flipped in the bottom. So just make your exponent negative, and then it'll work. Any question on that one?
Isn't it 2? The negative 2?
Yeah. Yeah. I'm just seeing if you're paying attention. No, I messed up. Yeah. So I always do that. People always say 5 times 5, and I always say, no, careful, it's not 5 times 5, it's 5 squared, so it's 2. I made the same mistake. So yes, it is negative 2. Any question on that? And I think you said squared. So you said it right, and I wasn't. I didn't write it correctly. All right, let's try this one. So another log equation. This time the variable, well, before it was by itself. Now it's in the argument. So it's going to be a little different, but we're going to solve it the same way. So Nate, how would I write that in exponential form?
So that would be x equals 5 to the power of 1.5.
That's it. You just do that up. 5 is your base. Logarithm equals the exponent. Argument ends up alone. So you just type that in on your calculator. 5 to the 1.5. They didn't ask us to do it out, so I'm just going to leave it like that. Especially if this number gets really big. Like if 1.5 was like 20.5, 5 to the 20th something power, that'd be huge. You wouldn't have to do that out. So I'm just going to leave it like that. All right, so we did one where the variable was by itself. We did one where it was the argument. Let's do one where it's the base. And then we'll finish up with the last thing for today. Okay, how would we write this one in exponential form? Say it.
X squared equals 3.
Yep. X is your base. Logarithm equals the exponent. Argument ends up alone on the other side. Now, this time you can't add, subtract, multiply, or divide to get x alone. What would you do on both sides to get x alone? Emily?
Take the square root.
Yeah, take the square root. Again, I'm not going to do it out. I'm just going to leave it like that. So once you get the hang of changing log form to exponential, it's really not super hard. I think we've done things that are much harder with algebra than that. Any questions on that one? Okay. So last thing, it's not the last thing in the lesson, but it'll be the last thing we do, is some different properties of logarithms. These are just special patterns that when they come up, you automatically should know the answer to the problem. These don't involve arithmetic or calculations at all. They're just special patterns. In the formulas I'm about to give you, I'm going to use a variable, a, and it has to be a positive number, not 1. So if I give you any homework problems and you have to use these formulas, It'll always be positive numbers that are not 1. Okay. So there's our first property. It says a to the log base a of x equals x. What's happening there is because something matches up, you're getting a lot of canceling out. Okay. Don't write what I'm about to in your notes, but because this base and this base are the same, so it could be like 2 to the log base 2, or, well, that's exactly the problem we're going to do. Because these numbers match, all of this stuff cancels out, and the only thing you're left with is that, and that's your answer. Okay? So it's just a special pattern. If you had something like 12, now the pattern doesn't work. Okay? You have to have the same number in each spot. Okay? And then it cancels out. So I would just leave it written like that in your notes. Okay. Second special pattern also has to do with some things canceling out. And it says log base a of a to the x equals x. Because this and this match, all of this just cancels out. And the answer is what's sitting right there. So when we do a problem, we're going to do one that looks something like this. Log base 0.2 of 0.2 to the negative 4. The log and the 0.2's cancel out, and whatever is left is your answer. It's just a special pattern that comes up. All right, let's look at this one. Anytime you take the log and the base and the argument are the same, the answer is 1. So if I said, what's log base 3 of 3? 1. Log base 6 of 6? 1. There's reasons why these are all true. The reasons aren't really something I'm going to go through right now, but if you want to know, I can tell you why at some point.
Since it was like the exponent, would you need to flip the -4 or do you just leave it?
No, you just leave it. Yeah, whatever is sitting right here in the last property, that is the answer. Just like that is the answer. Okay. And then the last property says that if you take the log of 1, the answer is always 0. Doesn't matter what the base is. So if you said to me, what's the log of 1 base? 0. Doesn't matter. I would just say 0. I don't even need to know the base. Okay, so we'll try one of each of these, just make sure we recognize the pattern, and then that'll be the last thing for today. And then there's really only about 15 minutes left on this one, which we'll combine with 5.4 part 2 on Monday, and 5.5 we'll finish on Tuesday. Okay. So let's see if we can recognize which property this one is. So the properties are 1 through 4. Which one is the first one? A. It's property 1. It's where you have a log up in the exponent, and the base on the log matches the base down below. So when you do that, something's going to cancel out, and what are you going to be left with? Pi. That's the answer. That's it. You do? Yeah, I like key lime pie. But I like chocolate pie too. I like pie. I eat anything really. I like dessert. All right, let's look at B. Log base 0.2 of 0.2 to the negative 4. This is the whole key that makes this one work. What property does that one look like? That's property 2, because now the log isn't up in the exponent. It's just right on the line with everything else. So what would be the answer there? Negative 4. Okay, let's look at this one. This one looks a little different, but it is one of the properties. If you remember something about ln. How can you rewrite ln so it's showing the base that it's hiding? Yep.
Log E.
Log base e. This part Just replaced that part. Now copy the rest of it down. E to the kt. It's the same property we just did before. Bases and bases match. Did you send that? I can see.
Oh, yes.
So what's the answer to C? KT. Whatever K times T is. We don't know. Let's do log base 5 of 1. 0. That's property 4. The log of 1 is always 0. Okay. And let's do log base 12 of 12. The answer there would be 1. It's the special pattern number 3. X equals 1. Any question on the special properties? Okay. So the last thing we'll look at next time is combining and splitting logs, which again, there's about 4 slides left. So for homework, 1 through 6 should be okay. 13 through 16, that's okay. 21 to 23, that one should, no, don't worry about 22 and 23. And then I think the rest, actually 25 is okay, 26 is okay. Don't worry about 27 though, just 25 and 26. And then 29 to 32, that's all stuff we didn't get to. So 29 to 32 you'll have next time. If you want to write it down now, you know what, maybe you should just write it. But I'll check that. 29 to 32 I'll check on Tuesday. So I'll check everything that's in that box on Monday along with the homework that was due today, because I didn't check that. So I'll check 2 homeworks on Monday.